Hello friends, in this module we will be learning about permeability of different plastic films and multilayer materials and the basics of calculations related to permeability of materials and methods desired for the measurement of permeability related to oxygen barrier properties and water vapor barrier properties. So starting with the transport behavior of substances in polymeric materials has become progressively more important in recent years with the widespread use of plastic films and rigid plastics for food packaging. The selection of plastic materials for food packaging applications with strict design specifications relating to their transport behavior requires knowledge and appreciation of many features which affect those phenomena. There are many examples of food packaged with an obvious lack of proper consideration of the effects of environment on the properties or of limitations forced on performance due to unfavorable transport characteristics. The plasticization of polymers by sorption of ambient vapors or liquids causing subsequent decrease in mechanical properties and the loss of beverage components are few of many examples which may be cited. An objective of research in this field is to establish mechanisms and expressions relating solubility and transport with the molecular properties and characteristics of the components. So, starting with permeation. Permeation through a film is a three-part process. First one is solution or absorption of penetrant into the polymer surface, migration or diffusion of penetrant through polymers, emergence, desorption of penetrant from opposite surface of the polymer. Absorption and desorption depend on solubility of the permeatant, and solubility is greatest when penetrant and material have similar properties. Other relevant theories comprises Graham's law stated in 1833. It states that the velocity of diffusion of a gas is inversely proportional to the square root of density of material. Second law is Fick's law. It states that the quantity of diffusing gas is proportional to concentration and time and inversely proportional to the thickness of material through which it is diffusing. And the last one is Henry's law stated in 1803. It states that the amount of gas absorbed by particular volume of a liquid at a specified temperature is directly proportionate to the partial pressure of the gas. In practice, the film of packaging material may comprise more than a single polymer, and there may be discontinuities in coatings, pinholes in films, variation in molecular structure and degree of crystallinity. The penetrant molecular size, shape and degree of polarity and ambient conditions are relevant. These are all factors which affect diffusion and solubility, which in turn have a direct impact on the permeability. The permeability of plastic film to water vapor and common gases like oxygen, carbon dioxide and nitrogen has been measured by standardized test methods. Oxygen can cause oxidative rancidity in oil and fat containing food products. Water vapor permeation into a product may cause a loss of texture, and outflow of water vapor from a product through the packaging may cause dehydration, textural changes and loss of weight. An example of the latter would be a plastic film wrapped cakes or bread which would lose moisture in storage prior to sale, where a negotiation has to be made in balancing weight loss in storage with initial weight and the water vapor barrier protection provided by the plastic film. In this example, in an addition to flavor retention and texture, the actual weight at the point of sale would also have to be meet appropriate regulations. The results of permeability tests gives direction with respect to the choice of material for the packaging of specific food products. Some other possible penetrants and the effects of presence of polymer additives can lead to unexpected results. It is still necessary to carry out shelf life tests to establish performance of packaging material in practice with the food under consideration. Under steady state conditions, a gas or vapor will diffuse through a polymer at a constant rate if a constant pressure difference is maintained across the film. The diffusive flux J of a permeate in a polymer can be defined as the amount passing through a plane surface of unit area normal to the direction of flow during unit time, that is J equals to Q divided by A multiplied by T, where Q is the total amount of permeant which has passed through area A during the time T. Looking at the desired properties of good packaging material or good barrier material. To be good all-rounder barrier material, the polymer must possess some of the properties, which includes some degree of polarity as found in nitrile, chloride, fluoride, acrylic or ester groups, high chain stiffness, inertness to the permeant. Polymers containing polar groups can absorb moisture from the atmosphere. This has the effect of swelling or plasticizing the polymer and reducing the barrier properties. Close chain to chain packing ability got the molecular regularity, crystallinity or orientation. Linear polymers with a simple molecular structure lead to good chain packing and lower permeability than the polymers in which the backbone has bulky side groups, leading to poor packing ability. The higher the degree of crystallinity, the lower the permeability, because crystalline regions are less permeable compared with amorphous regions. Orientation of amorphous regions decreases permeation by about 10 to 15%, while in crystalline polymers reductions of over 50% can be observed. Some bonding between chains. Cross-linking of polymers restricts their mobility and thus decreases permeability due to the decrease in diffusion coefficient. For example, in the case of polyethylene, one cross-link about every 30 monomer unit leads to 1/2 the reduction of diffusion coefficient. The effect of cross-linking is more prominent for large molecular size permeants. We will see how to calculate permeability of multi-layer material. Considering multi-layer material as a series of membranes together in one series. So, in that the area of the membranes will remain same, the rate of transportation or permeation will remain same, but the thickness will be varying. So, if we consider the thickness together, then replace it in the equation, we will get the proper idea. By arranging previous equation and writing it for the case of permeation through multi-layer material, Qt into Xt divided by T into At into Pt equals P1 minus P4, that is delta pi. Now, since P1 minus P4 equal to P1 minus P2 plus P2 minus P3 plus P3 minus P4, therefore, Qt into Xt divided by T into At into Pt equals to Qt divided by T into At whole multiplied by in bracket x1 by P1 plus x2 by P2 plus x3 by P3, and xt by Pt equals x1 by P1 plus x2 by P2 plus x3 by P3, or permeation coefficient Pt equals xt whole divided by x1 by P1 plus x2 by P2 plus x3 by P3. Thus, if the thickness and permeability coefficients are known for each layer and provided that the permeability coefficients are independent of pressure, then above can be used to calculate permeability coefficients for any multi-layer material. If they are not, then the differing permeability coefficients will be obtained depending on the positioning of the layers. The standard methods for gas permeability measurements through plastic material specified dry gas, but in practice the films are almost used in humid conditions, and for materials such as ethylene vinyl alcohol copolymers, the oxygen permeability is dependent on the humidity. In such a case, the above equation cannot be used directly, since P2, the permeability coefficient of center layer, will depend on the average partial pressure at the center. An equation for forecasting the average partial pressure at the center of a multi-layer material containing a water sensitive center layer can be derived as follows. Consider again the case of 3 layers in series, but this time assume that the oxygen permeability of the center layer is moisture dependent and that the direction of water vapor flux is from outside to inside. Since the partial pressure of water vapor will not be constant across the multilayer, the equation must be modified to include a term for the partial pressure difference and the thickness. WVTR equals Q divided by A into X into T whole multiplied by delta P. Now, since the area A and time T will be the same for all the 3 layers, the equilibrium WVTR between the outside and center layers can be calculated as Q1 by X1 in bracket P1 minus P2 equals Q2 by X2 in bracket P2 minus P3. Similarly, the equilibrium WVTR between the center and the inside layer is Q2 by X2 in bracket P2 minus P3 equals Q3 minus X3 in bracket P3 minus P4. The average partial pressure of the center layer will be Pc equals P2 minus divided by 2. Simultaneous linear solution of equations for P2 and P3 and substitution in above equation will get average partial pressure of the center layer. By the data of Pc, the permeability coefficient Pc of the center layer can be determined at this partial pressure, and equation for Pt can be used to calculate the overall permeability of multi-layer material. Now, measurement of gas permeability. There are many methods for measuring permeability. Some important methods will be considered in this module. For a complete understanding of principles behind permeability measurements, it is important that the meaning of two terms which are constantly used, total and partial pressure of gases in a mixture, is clearly appreciated. In constant volume, total pressure exerted by gases present in the sum of partial pressures of each of the gases, a discovery made by John Dalton and known as Dalton's law. The partial pressure of any one of the constituent gases is the pressure which would result if the particular gas occupied the same volume by itself, that is, each gas in a gas mixture behaves independently of other gases. The permeation rate of a gas through a polymeric material is function of partial pressure difference of that gas across the material and not of the total pressure difference between the two sides. First one is pressure increase method. The ASTM standard method for measuring gas transmission rates and permeability of flat films is labeled as D1434. It includes the monomeric method, which utilizes the Dow gas transmission cell. The film is backed with a filter paper and sealed with an O-ring. The pressure in the receiving compartment is measured with an open-ended mercury manometer. Detailed descriptions of the calibration and testing procedures are given in ASTM method. The corresponding British standard is BS 2782 part 8 method 821A. On condition that the pressure on the high pressure side remains much larger than on low pressure side, the pressure difference remains constant and the permeability coefficient can be calculated as below. The slope of the straight line portion of the plot of pressure in mm mercury on the low pressure side versus time is determined and substituted into the following equation, where P equals delta PL by delta T multiplied by VL by 760 multiplied by 273 by capital T multiplied by X by A, where VL is the volume of low pressure side, X is the thickness of film, capital T is absolute temperature, and A is the film area. Another method is a concentration increase method. In this method, a partial pressure difference through the film with respect to test gas is created without change in total pressure, thus avoiding the need for rigid support of the film. A partial pressure difference is maintained by sweeping one side continuously with the test gas and keeping an inert gas on the other side into which the test gas diffuses. The concentration of the diffusing gas can be measured by chemical analysis, gas chromatography, thermal conductivity or special electrodes. As the method of measuring the concentration of test gas can be specific to that gas, equipment can be developed in which the relative humidity of both the test and inert gases can be controlled. This is of main importance when measurements are carried out on films whose gas barrier properties are related to humidity or moisture. Instrument in extensive commercial use for estimation of oxygen permeability by the isostatic method is Mocon OX-Tran. An advantage of this instrument over the permeability cell is that the permeability of not only flat film, but also containers, bottles, pouches, tubes, etc. can be measured, thus allowing the analysis of possible adverse effects of machine processing, printing and distribution. The use of this instrument is included in ASTM D3985. The OX-Tran has a 2-chamber measuring cell between which the test film is placed. The gas stream of known oxygen partial pressure is passed through one of the chambers. Oxygen free carrier gas is passed through the other chamber to a coulometric detector. A separate part of the instrument is fitted with 2 openings for the carrier gas over which containers can be fixed and sealed. A glass dome is located over this arrangement into which the oxygen flows by means of filling tube. Modern Controls Inc. has designed an instrument for measurement of carbon dioxide permeability. It is known as Permatran C. It is similar to construction to the OX-Tran, but it uses pressure modulated infrared detector. The next method is volume increase method. In this method, the change in volume at constant pressure because of permeation of gas through the film is measured. Variable volume permeation cells are often used for rapid estimation of relatively high steady state permeation rates. Though the volume increase method is simpler to implement but less sensitive than the pressure increase method, it is rarely used for high pressure time lag measurements. Volumetric methods are used relatively infrequently compared with the use of pressure increase or concentration increase methods. Detector film method. It is a method for measuring permeability of films which requires little equipment and is both rapid and accurate. Has been devised. The principle of the method is a plastic detector film saturated with a reagent which is sensitive to the measured gas. The film having an absorption spectrum that changes with the gas or vapor when absorbed. It thus suitable for spectrophotometric measurements. The detector film is sealed between 2 pieces of test film in a simple cell so that the permeation rate of the penetrant gas or vapor can be readily measured. The detector film can measure much less than the minimum detectable quantity of oxygen determined by most other methods, and therefore allows the use of either smaller film samples or more rapid permeability determinations. The oxygen detector consists of a cast film of ethyl cellulose containing dimethyl lanthacam DMA and erythrocene. On absorbing blue light, the erythrocene can trigger oxygen dissolved in the ethyl cellulose to form singlet oxygen, a reactive form of oxygen. Singlet oxygen diffuses to a neighboring DMA molecule and reacts with it. Thus, The disappearance of DMA is monitored in the UV, which is measure of oxygen consumed. As the ethyl cellulose detector is highly permeable to oxygen, it is capable of measuring very low rates of oxygen permeation. Now, we will discuss about water vapor permeability. The standard method to determine water vapor transmission rates is to place a quantity of desiccant in an aluminum dish which is covered with a sheet of material being tested and sealed in the same position with wax. Dish is then placed in a closely controlled atmosphere of either 25 plus or minus 0.5 degree centigrade and 75 plus or minus 2% RH for temperate conditions, or 38 plus or minus 0.5 degree centigrade and 90 plus or minus 2% RH for tropical conditions, and the increase in weight noted as function of time. If the points are plotted out, they should fall more or less on a straight line, since dP is constant throughout the test. To convert WVTR into permeance, it should be divided by driving force, that is dP. This method has several disadvantages, including the length of time needed to make a determination of 2 and 14 days and the lower limit of the useful range of about 1 gram per meter square per day for a typical packaging film. Another disadvantage is that depending on the desiccant, dP may not remain constant during the test period. When using anhydrous calcium chloride, the partial pressure of water vapor in the dish remains below 2% of the vapor pressure of water at test temperature. While in case of silica gel, the partial pressure of water absorbed on it increases with coverage. Newer type of film detector to measure the rate of transmission of water vapor has also been developed. It comprises of transparent cellulose film which becomes bright blue when soaked in cobalt chloride solution and dried over calcium chloride, but rapidly turns pink on exposure to high humidity. A humidity cabinet is used to provide the partial pressure gradient through the test film, which is sealed in the same way and in a shell of similar design to that used to measure oxygen permeability. The change in absorbance of the detector film is measured at 690 nanometer, and from this the quantity of water absorbed by the detector film and hence WVTR of the test film can be calculated. Good results have been obtained using this method. Odour permeability. The permeability of packaging material to organic vapors is of substantial interest, predominantly where the contents of the package has to be protected against foreign odors or where there is a prerequisite that volatile flavoring materials are not lost from the package. The measure of flavors found in some food products may result from packaging material itself or may permeate via the packaging material from the outside environment. In other situation, food may contain highly desirable but volatile flavor compounds whose loss from the packaged food will reduce its quality. In both situations, suitable tests must be undertaken to select materials which have the desired odor barrier properties. There are no standard methods for measurement of odor permeability. A number of methods have been described for vapor permeability measurements, although many of them are only suitable for use with saturated vapors only. A sophisticated instrument for studying the transport of aromas in polymer films has been described, which utilizes a mass spectrophotometer to detect the permeant. Temperatures up to 150 degree centigrade and relative humidity from 0 to 100% can be used, making it possible to obtain data on the likely aroma, flavor and odor permeation of polymeric materials used in retortable pouches. A method for quantitative evaluation of the aroma barrier of packaging materials has been developed, which uses a permeation cell similar to that described for the concentration increase method. Nitrogen gas is bubbled through the liquid permeant and then passed with the permeant vapors through the cell. The concentration of the permeating vapor and related humidity are monitored by gas chromatography. A common odor penetration test involves packaging various odoriferous substances in pouches made from the test materials. The pouches are then placed in a clean glass bottle and sealed by crimping with aluminum foil. After storage for a fixed time, the bottles are sampled either by gas chromatography and mass spectroscopy or by sniffing using a sensory evaluation panel. By these results, it is possible to rank a range of packaging materials according to their odor barrier properties. There are various methods for determination of permeability of multi-layer packaging materials, but particular methods have often been lost and then rediscovered. Their origins are forgotten. For example, the isostatic method has been reinvented many number of times, most recently in 1973 since Mitchell used it in 1831. Although the permeability of the permeant gases and of water vapor through many packaging materials are well known, there is a lack of data for the permeation of organic vapors. Much of the published work has involved the use of saturated solvent vapors, and although this data is useful in estimating how well a packaging material will withstand accidental high level contamination, it is not generally valid to use such data to estimate permeation rates at the very much lower levels of vapor encountered in typical relating situations. So, there is a need of work to be done on the measurement of permeability of organic vapors or odors compound in the actual retail situations. So, friends, in this module we have learned that how to measure the permeability of multi-layer materials and how to measure the oxygen transmission rate and water vapor transmission rate. There are many methods for determination of these rates, but some are quick and some are laborious or time consuming. But still some work need to be done on determination of odoriferous material or flavor transfer rates. Thank you.